Hello everyone. Welcome to our MSJ Systems Design meeting. And today we're going to be talking about databases and specifically the pros and cons of databases. So the question that we want to be able to answer by the end of this lecture is basically kind of how Google pops 1 billion results in a second. So we'll see throughout this lecture how Google exactly does that. All right, so this will be today's table of contents of what we will be reviewing today. So first off, we'll give an introduction or overview of the databases. The second part, we'll go over what the fundamentals of the databases, functionality and features of the databases. And the third part, we'll be talking about relational databases, which is basically a collection of items with predefined relationships. Fourth topic will be non-relational databases and types. And our last part will be conclusion, which will be summarizing basically everything we went over today. Yeah. All right, cool. So you guys might be wondering what a database is. So I guess the introduction database is an organized collection of structured information or data typically stored electronically in a computer system. So databases revolve around the organization of data depending on the type of data and the relation of the data being stored. So databases are an integral part of the largest technology applications in the world and companies such as Google and Facebook, as it greatly impacts their scalability, speed, and consistency. So this definitely makes sense since a lot of companies now want to store all of your data, right? But they need somewhere to actually store. So this is where databases come in handy.
Okay, so now that we've introduced the topic, let's go into the actual functionalities that they support. So when there's a bunch of actions that are integral to the database itself. One, it can contain data. Two, you can update and remove data from it. And then you can return data according to what the query is or what the user requests. It'll return specific data based on what they want. And then administer the database. And then what a database needs to fulfill is it needs to operate with efficiency, accuracy, and it needs to be consistent because you don't want a database that returns wrong results or you can't depend on it at all times or it's down a lot. So there's a lot of things that it must meet. So one way that we can talk about databases using the CAP theorem, which essentially runs with three main features due to this acronym. So consistency, which means that every node inside your database has to be able to return some value. Availability, meaning that and consistency meaning every single node has to return up-to-date information, it has to be up to date. But availability also means at any time it can produce a response, but it's not concerned about the accuracy. It's just it always needs to be able to return something when you call upon it. And then partition tolerance, meaning that even if there's broken node connections, your overall system will still be able to operate. So there's also many ways we can describe a database based on these terminologies. And partition tolerance is basically always required. You're going to expect that from any of your databases, but you can't expect both consistency or availability. You kind of have to choose both one or the other when you're making your database. So a CP database is essentially that means that you have consistency and partition tolerance. So basically this stresses that all your information displayed is up to date, but then availability is just it basically means that all the time you have some feature on your website that can be interacted with, it'll never be down basically, but it's not concerned with the accuracy or how up to date the information is. So a lot of times you're going to have to sacrifice one for the other, and it just depends on your specific use case. Okay, so another part of databases we can measure is the transactions, and that's just a single unit of work, which guarantees that it either completes or not. And this is vital because you don't want to interact with a database midway and then your process corrupts and then you lose important information. So that's why it's important that transactions are kind of like a Boolean, similar to that, it either completes or it doesn't complete its operation. Okay, so we can describe it with ACID transactions. This is a way we can define the properties of a database transactions. So let me define the acronyms. Atomicity means that you can guarantee the completion or on completion, like I mentioned before, of certain transactions on your database. Consistency meaning that you have predictability regarding what changes you make. So like you have like basically like if you have a certain data type that you want to be entered in, like it'll always maintain this. Like it's not gonna go off in some variable. So like so basically the like for like the database, like it has to be consistent, it has to be similar in its action every time. Isolation meaning like each event is not affected by another event. So if there's a bunch of transactions occurring at the same time, one transaction will affect the actions of another. And then durability meaning all your changes will be saved. So all your changes will be reflected and it won't be just like removed or anything like that. Okay, another aspect of databases are the schemes, which is how we can like define the shape or like the general structure of our database. And it guarantees that queries return data in a specific format. So like for example, like a specific type of data type or like it guarantees that'll be in a certain format or like a certain operation to retrieve the data. Like that's what a schema is. So like schemas, it basically just allows you to like standardize like how like a query returns data. However, like this type of process can be like very computationally expensive, as mentioned there, and it can also be difficult to scale whenever you're trying to grow. And this leads us to another topic that we actually discussed last week, which is like scaling. So vertical scaling deals with increasing the capability of one certain computer, or like in this case, we can talk about increasing like more RAM disk or like SSD resources. And then horizontal scaling is just adding more computers to a cluster. So that's like increasing the computer count. So there's different types of scaling involved with databases. But let's go over some example problems just to like apply this to like more real world like applications. So if there's a product listing app like Amazon, where you can determine whether like you want to buy items or like it's posted or not. Like what type of database do you think would be better? Like a CP database, like I described before, an AP database, stressing availability. So like in terms of my thought process, this is how it goes. So like if you're on Amazon and like there's multiple people like buying the same product, you don't want to like you don't want one person to buy it, but then like another person also like, and then it runs out of stock, right? And then another person buys it and then they're allowed to buy it because that would cause some issues. So you always want to make sure that your information is consistent or up to date on the website because you don't want to have like conflicts with different buyers purchasing the same item, but like it doesn't go through. However, availability, I would say it's not as important because like you just because your item's like always up for sale, like if it doesn't contain accurate information, it could be like very detrimental. It could cause a lot of complaints. So as it says here, it does agree. So consistency is important. Yeah, as it says there, it does have an example. Two or more shoppers purchase the same product. It wants up-to-date information so that you wouldn't run into like issues with multiple people buying like a out of stock product. Now for another question, are the C and cap theorem and acid the same? Well, while they do stand for the same thing, they actually have different meanings. So they do both stand for consistency. However, consistency in the cap theorem means that like all the nodes return up-to-date information. However, in acid, it means like that it consistency just confirms that like all transactions on a database will take it from one valid state to another. And as I said, like there's no like in between, like it always has a consistent result in how it affects your database, the transactions. Okay, let's go on to the next section.
All right, so next let's talk about relational databases. So essentially here, the type of data being stored is going to be organized in kind of like a section of rows and columns. These are how the data entries are going to be formatted with predetermined data types. So these are often referred to as SQL or SQL databases over here, or which also stand for structured query language databases. And over here, basically the requester is going to tell the database what it wants, and then the query planner is going to determine the method of retrieval. Also, for these type of databases, indexes, in which like a copy of column of interest that we want to like basically access data from can be utilized to search for a specific column as quickly as possible. And there's also going to be concepts that we talked about earlier from like CP databases involving cap theorem, consistency, and partition tolerance. And this is also due to like the relational model enforcing a validity of the database. So for example, if you want to kind of visualize a relational database, think about it as like a table. SQL databases often are formatted in like some structure like a table. So we might have something like, let's say we want to buy something from the store, right? Or like make sure, like let's say actually that we're trying to have a user log into a website and they need an account to do so. So in our database, we could store like the users, and the users can have predetermined like different types of data, like their username. So they may have like their username over here, and that's going to be like a string type, right? And they're going to have, they might also have like a password, which is also going to be a string, something like that, right? And they might have like an age, which is going to be an integer, something like that. So that's kind of the idea behind the databases here. And we could have people that are going to be stored inside this database. So let's say like we want to store like Alice, for example. She can enter in her username when she's registering, like Alice 4521 or something like that. I don't know. It's just some random username. Just create a password, but basically the same idea. It's a string. And she might store like her age might be like 23, something like that. So basically, SQL databases are really convenient for kind of storing data like this, where you just have everybody having the same type of consistent data, and you can just have new rows for each entry, and each column is kind of set in stone for like the type of database, a type of data that it stores, and like what type of like data type it is. Okay, so next let's talk about like when we should and when we shouldn't use relational databases. So as I said earlier, relational databases like SQL databases, they're really, really consistent in terms of the data they store, in terms of the fact that like they're stored in a table. So we should use them when there are many to many relationships between the entries, and data needs to follow a predetermined schema. So schema is essentially basically what I outlined earlier. So the tables having several columns, like the structure of the table is basically going to be the schema. So it's going to have a predetermined schema and like essentially the same data types being stored each time, right? So relationships between the data always need to be accurate. So what I mean by this, and this will basically tie into when we don't want to use relational databases, is let's say like, again, with that table example, that they're logging in information, like a user is entering their login information to go into a website. We don't want to store, like if we have, when we're having the user sign up for this particular service or website or something like that, and having the user's information being stored in the database somewhere, like somewhere over here, we don't want the user to have like inconsistent data in the table, right? We don't want, like, for example, we have like a name over here, an email over here, a password here, an age over here, and we don't want to have like, we don't want to start making things optional. Like, you know how when you guys go to a website, sometimes some fields are optional and sometimes like, okay, you must fill this out, you don't have to fill this out, etc., etc. Don't it's like suggested that you don't use SQL databases for this type of stuff, and like basically relational databases, because the data is not going to be consistent, and you don't know whether like a specific table is going to, each like specific row, each entry of the database, you don't know if it's going to have like that field or not, because it's optional. It's not required, right? Originally, if we have a database in which it's like relational and the structure is the same, then we know that every single user is going to fill in all their data and all the data is going to be consistent, which is why it's so like accessible. And that's like the use case of this particular database, right? But if we use a relational database over here, we want to avoid having inconsistent data. Like some people have like specific entries that they don't put in and stuff like that, because then it's inconsistent. So when not to use them, basically that case, they have low flexibility on how you are shaping the structure of your database. It's kind of set in stone. And also it doesn't work well with horizontal scaling because it becomes slower with the network communication. And overall, there's some like popular examples of relational databases, Oracle, MySQL, where like most people pronounce it MySQL, and also PostgreSQL. These are some common relational SQL databases that you can encounter and use when you're kind of figuring out your structure of your system particularly.
Okay, so there are two types of databases in general. So like there are relational database and there are non-relational database. So there's like the relational databases are what Brian just said, and every other types of database are categorized under the non-relational database type. So there are many different types of non-relational databases. So for example, like there's a hierarchical, and there's document-oriented, and there's a graph, and there's also search engine database. And keep in mind, there's also many other different non-relational database types, but those are like just the main or the major non-relational database types. And what they are used for are they are used in optimizing for specific use cases that require some forms of scalability, schema flexibility, or specialized query support. So this is the first major non-relational database type, hierarchical database. So what it is a database that looks kind of like a tree. If you have studied computer science and you learn some fundamentals about graphs, nodes, and edges. So what a hierarchical database is, it have a root node at the top, and for all the nodes that are connecting to this root node are the first level child, and every other nodes that connecting to the first level child are second level child, and so on. So this is a tree graph. So unlike a relational database, like this database, you can only have one data having a relationship with either the node above it or the node below it. Like you cannot have relationship between adjacent nodes that are in the same level. So it supports only one-to-many relationships. It's really simple and it's fast, it's easy to use. Like the entire schema is shown like in the slide right now. So, but it does not provide like very consistent feel or like a strong like schema like the relational database did. So there are some useful usages, like in case where like you require a lot of reads on unstructured data, and they're commonly used in information management system or like user generated content in case like you have a profile like in a website and you upload like images or like text or like videos, and there can be like they can be considered as like child nodes of the user node. And there are some examples of like hierarchical database. So IBM IMS is a popular one. There's also a Redis database that's also a hierarchical database. And the next one is object-oriented database. You probably know this as JSON because JSON is an object-oriented database. And if you have done any sort of web development, you will see like JSON a lot. So what object-oriented database is also pretty similar to a hierarchical database, but instead of just like nodes that are connecting towards each other, all the nodes that are under one child node, one first level child node, are in the same document. So like a document-oriented database is a collection of documents where each document can have like child nodes inside of it. And the good thing is that it provides more relationships than just like typical hierarchical database. And it's also fairly easy to use and very simple to set up. Some good usages is for like keeping track of like data that are not very particularly defined, but still have some sort of structure. And it can be used in storing information about books or like a catalog of something, or also user-generated content. So there are some example of databases that are object-oriented. So MongoDB, that's one, and also JSON. So the third database that's non-relational is graph database. So unlike hierarchical database, this database allows nodes to connect other nodes without any like first level, second level, or third level restrictions. So any node can form a relationship with any other node, and you can form as many relationships as possible. So all the objects of the can be considered as nodes, like you can store information in the nodes. But what's special about graph database is that this database prioritizes relationship information. So you can, if you have some sort of data that that you have a lot of query about the relationship between some forms of information, graph database is the database you want to use because it can process the relationship between different types of nodes really fast. It's a good database. It have a lot of relationship, like the relational database, but you don't have to provide like a predefined schema in order to use a graph database at the start. So the usage for it is that it can provide really fast relationship queries, and some examples are recommendation system and social networks. So if you log into Facebook, like you will see like friend suggestions. The Facebook uses some form of graph database that sees like all the connections you have with your friends and suggest like other nodes that are friends of your friends and suggest to you so you can form friends with them. And some examples of graph database are Neo4j. This is a really popular one. It's currently, I think, took like the major market share of the graph database. And there's also dgraph and Amazon Neptune. Next slide. So the last one is search engine database. So it's database used by search engines like Google. So what it is that it's specifically built for text search over large unstructured text data. So like it's really useful for like searching like text on text files rather than images or videos or audio inputs. So it's a data structure built to support like distributed and parallel processing. So if you have like multiple servers, this database can support that. So it's really good for horizontal scaling. And some usages are like good for event logging, keeping track and lookup items. And some examples are like website search, like DNS lookup. So once when you enter like a web domain, like in your browser, that's a DNS. So it can process DNS lookup really fast. And some examples are Elasticsearch, Splunk, Solr, and Algolia.
Okay, so now I'm gonna go to conclusion, which I'm gonna talk about what we've learned so far in this lecture, and then the industry application, which specifically to Google, how they utilize this technology. So we've learned about the different types of databases and the different features that each one provides, and this will allow us to better make choices regarding like for a specific circumstance or application, which one will suit our needs. And this will assist us in our entire system design journey because the whole point is to have customability and be able to determine different parts that will allow us to add to our needs for a specific system. So basically this customizability and all these different features and options we have will allow us to expand on our specific application if we want to build one. So now regarding Google itself, how do they use databases? So they specifically use databases to store a lot of different information all over the internet, and this will allow them to have suggestions to bring up whenever you search something up. So as it mentions on the right, we can actually see their specific process of how to power Google search. And also another interesting thing to note is it suggests 1 zillion results in a second. So obviously they have a lot of scaling and a very large and also a very fast database to power the system. So looking at the right, we have 3 different steps. So crawling is the first one, which they take a bunch of text, images, and videos from on the internet with crawlers, which are an automated program, and then it assigns this information into the Google Index, which is a large database. And an index basically allows you to just speed up your search. inside database, as we mentioned before, like previously in this lecture. And now that all this information is stored, we can finally use serving search results. They do this by returning information based on the user specific query, based on what they request. Then it'll return the relevant information from this database of information. I believe that they also use like a NoSQL database as well, because it allows for them to scale better and there's no like restrictions based on the specific data types or like any like restrictions. Essentially, NoSQL has like no specified format or like boundaries, so it's better for like an expanding business like Google. And that's pretty much it for how databases relate to Google. And because like it's used so prevalently, like all over the tech world, you can even use it yourself for your own projects, and it'll definitely help you out in that regard. All right, so that's the end of our meeting. And thanks for joining in. If there's any questions, we'll answer those. And otherwise, we'll just end it. So yeah, are there any questions? No questions. Okay. Okay, thank you for coming. And that's basically it. Okay, see you guys, see everyone later. We'll be giving our final lecture of this summer very soon in 2 weeks. So yeah, looking forward to that. And then we'll see you guys for the school year coming up. All right, bye everyone.